Solving for Schrodinger's equations, people found that there were a lot of different solutions for these equations. So that meant there are a lot of different types of orbitals. So because of this, they came up with a method of distinguishing different orbitals, and that's what these quantum numbers are for. They're for letting people know which orbital you're talking about. So there are three main quantum numbers. There's a fourth one which has to do with electron spin, but that one's really not that important right now. So the three main ones are the principal quantum number, the angular quantum number, and the magnetic quantum number. Now the principal quantum number tells me the size and the energy level of the orbital. So if I have 1s, which is one that most people are familiar, it's just a sphere. As I go further and further out, the second shell becomes a little bit larger and it's higher in energy, and the third shell is larger and higher in energy than the second shell. So here's a cross-section of, say, a 3s. Here the 1s would be in the middle, and then there would be a node where there would be no electron density at all, and then there would be the 2s shell, and then the 3s, and then, well, the other node first, and then the 3s. So as I get further and further out, the higher and higher principal quantum number, the larger the shell is, and the higher in energy it's going to be. The angular quantum number tells me what shape the orbital has. For angular quantum number 0, I get a sphere. For a 1, I get these three p orbitals, where they're just two, I guess, little bubbles that go forward, sideways, and up and down. For d, there are a set of 5 different orbitals. So there you get a good look at them. And they get more and more complicated as they go higher and higher. So those are the d orbitals. And the f orbitals are down here, and there are 7 different ones of them. And some of the shapes in the middle are a little bit bizarre, but the other ones make quite a bit of sense. I don't really know what causes those, but I would like to find out one day. And the magnetic quantum number lets me know which one of these orbitals I'm talking about. If I have, let's say, an angular number of 1, I've got 3 different orbitals that an electron could be in. And if there's only going to be 1 electron in all of these orbitals, then I gotta know which one it's in. So that's what the magnetic quantum number is for. The principal number has integer values, so it's 1, 2, 3, 4, 5, 6, 7, that kind of thing. The angular number goes from 0, 1, 2 to n minus 1. The magnetic quantum number, it is whatever the value of the angular number is, and then on the interval of minus to positive whatever that number is. So for 0, there's only 1, so I just have 1 orbital. For 1 of an angular number, I would get something like this: minus 1, 0, and 1. It's just the integer values between this interval of minus L and L. For the first one, I would just get 0, so I would just have 1 value. There's only 1 orbital. But this one, it would be like this. It's kind of designating them like this. So then I can let someone know which one of these I'm talking about. Its orientation in space is really the best description for a magnetic quantum number. So the principal quantum number, energy level, and size. Angular quantum number is the shape, and the magnetic quantum number is its orientation in space, because it could be in any one of these positions if there's only 1 electron or only a few. So that's what the idea behind them are, and this is how to set them up and get a designation for them. So I start with the principal quantum number of 1. My angular quantum number is n minus 1, so that would be 0. So this would be designated, this orbital would be called 1s. The magnetic quantum number is 0, and so there are 1 orbitals here. For n is equal to 2, since I've run out of 1s, I start with 0, I get 2s, magnetic quantum number is still 0, there's only 1 orbital there. For n is equal to 2 as well, I still have to exhaust all of my angular numbers. So I started with 0, but I have n minus 1, so I can have a possibility of 1 as well. So I go for 1. Now this makes this 2p. And the magnetic quantum numbers, therefore, are minus L to L. So I have minus 1, 0, and 1, so there are 3 orbitals. So 2p, minus 1, 1, or minus 1, 0, and 1. So that lets me know the shape, and it also has a designation for which orientation in space these are. So now that I've run out of 2's, then I move on to 3. Then I get a 3s orbital. I'm going to start with 0, 3s, 0 magnetic, 1 orbital. Then I'm going to have 1, it's going to be 3p, 1, minus 1, 0, 1, 3 orbitals, same thing, just a higher energy level. So these would be this here. And the different colors mean the different phases. That's a question. So this is, white could be positive, minus could be, or the yellow could be a negative phase, but that's what the different colors are supposed to mean. It's the different phases that it's in, since it's a standing wave. But here you can see it's a little bit harder to see because it's kind of small, but this is very obvious how it has the shells going around the outside, but basically it just adds another layer onto it. You can think of it that way. And then finally I go to 2, then I finally get into the D's, and then I have 5 different orbitals. And here is an example of what those would look like. These ones look pretty normal, but then you have this circle disc in the middle. I have no idea what causes that. That's what they tell me it looks like. Maybe I'll figure it out sometime. And then I can continue to go down. Then once I get to 4, then I'll finally get into 4F, and we can continue going on. 5 for S, P, D, F. We can continue going. I think it goes all the way up to 7, I think, and then we run out of elements. But this is how to work the quantum numbers and how to let people know what orbital I'm talking about here.